The sun can burn your skin from 150 million kilometers away. So why isn't space hot? Why can one side of a spacecraft bake in sunlight while the other side freezes in shadow? The answer is not that space is simply cold. The answer is stranger than that. Space is almost empty. Hold that thought for a moment, because everything you are about to hear depends on understanding one thing first. The way you experience heat on Earth is not how heat works in the universe. And once that distinction clicks, the question stops being confusing and starts being one of the most elegant things physics has to offer. Let's start with what you already know, because it is worth naming precisely before we take it apart. You are standing outside on a summer day. The sun is blazing. You feel warm. The air around you feels warm. The ground under your feet feels warm. You assume, naturally, that the sun is heating everything around it, including the space between you and it. If you put your hand near a fire, the air between your hand and the flame gets hot too. So the space between Earth and the sun should be scorching, right? But it is not. The average temperature of the space between Earth and the sun hovers somewhere between -270 and -455 degrees Fahrenheit, depending on where exactly you measure and how you define the measurement. That is close to absolute zero, the theoretical floor of temperature itself, the point at which molecular motion almost entirely stops. So the sun is releasing energy measured in millions of degrees. That energy travels 150 million kilometers, and the space it travels through remains essentially frozen. How? The answer starts with understanding that heat does not travel the way most people think it does. On Earth, heat moves in three ways: conduction, convection, and radiation. Conduction is when heat passes directly between objects touching each other, like a metal spoon warming up in a hot bowl of soup. Convection is when heat moves through a fluid, the way warm air rises and cool air sinks, creating the circulation patterns that make your oven work and your weather system behave the way it does. And radiation is when heat travels as electromagnetic waves through space, not needing any medium at all, not needing air, not needing water, not needing anything. Radiation is the only one of these three that can operate in a vacuum. And this is the key to everything. Space is a vacuum. Not a perfect vacuum, because nothing in the universe is perfectly empty, but close enough that the distinction barely matters for this conversation. The density of matter in interplanetary space is so low that if you took the best vacuum chamber humans have ever built in a laboratory, the emptiness of space would still make it look crowded. In that kind of emptiness, conduction cannot happen. There are no molecules touching each other and transferring energy. Convection cannot happen. There is no fluid to circulate. The only form of heat transfer that can operate is radiation. And radiation is selective in a way that the other two methods are not. When the sun radiates energy, it does not warm the space it travels through. It travels through that space as light, as electromagnetic radiation. And that energy only becomes heat when it is absorbed by something. The radiation passes through the vacuum, and the vacuum is unchanged by it. The photons are not warming the emptiness, they are moving through it. Think of it like a beam of light in a dark room. The beam itself is not illuminating the air it passes through, not in any meaningful way. You see the beam only if there is dust in the air, particles for the light to bounce off of. In a perfectly clean room, the beam is invisible until it hits a wall. The light is not making the air bright, it is making the wall bright. The sun does the same thing with heat. It does not make space hot, it makes things in space hot. Now let us make this concrete, because the abstract version is easy to nod along with and harder to actually feel. Imagine you are floating in space, roughly at the same distance from the sun as Earth. You are wearing a spacesuit, but let us set that aside for a moment and think about the physics of what is happening to your body. The side of you facing the sun is being bombarded with solar radiation. That radiation is being absorbed by your skin and your suit and the surface layers of your body. It is being converted into thermal energy. Without any mechanism to dissipate that heat, the temperature on your sun-facing side would rise rapidly, potentially reaching 250 degrees Fahrenheit or higher, depending on the surface and how long you are exposed. That is hot enough to cook. The side of you facing away from the sun is receiving almost none of that radiation. And because you are in a vacuum, there is no air to carry warmth from your hot side to your cold side through convection. There is no medium to conduct heat across your body quickly. The only way heat moves is through radiation from your own body, which is slow, and through conduction within your own tissues, which is limited. So you are simultaneously, in the most literal physical sense, cooking on one side and cooling on the other. This is not a thought experiment. This is the engineering reality that every spacecraft designer, every satellite engineer, and every mission planner at every space agency in the world has to deal with every single time they send something beyond Earth's atmosphere. Thermal management is not a minor concern in spacecraft design. It is one of the central problems. A spacecraft in low Earth orbit swings from brutal direct sunlight into complete shadow every 90 minutes as it circles the planet. The temperature swings involved are not small. They can range from plus 250 degrees Fahrenheit in direct sunlight to minus 250 degrees Fahrenheit in shadow. And this happens over and over, 16 times a day for something orbiting at the altitude of the International Space Station. Without sophisticated thermal control systems, electronics overheat in sunlight and become brittle and fail in shadow. Structural components expand and contract so rapidly and so dramatically that they crack. Fluids freeze and then boil. The spacecraft dies. This brings us to the moon, which is the most available and dramatic demonstration of exactly this principle that we have access to. The moon has no atmosphere worth speaking of. Its atmospheric pressure is so low that it qualifies as a vacuum by most engineering standards. And because of that, the moon has no mechanism to spread heat around its surface the way Earth does. On Earth, the atmosphere acts as a buffer. It absorbs solar radiation, spreads it laterally through circulation, retains heat overnight, and moderates temperature swings enormously. The oceans do the same thing on a global scale, absorbing heat during the day and releasing it slowly at night. The result is that even in a desert, the temperature swing between day and night is measured in tens of degrees Fahrenheit, not hundreds. On the moon, there is none of that. The lunar surface in direct sunlight reaches approximately 260 degrees Fahrenheit. That is hot enough to boil water at sea level on Earth. The same surface, in shadow or during the lunar night, drops to approximately minus 280 degrees Fahrenheit. The same rock, the same dust, the same material. The difference between direct sunlight and shadow on the moon is more than 500 degrees Fahrenheit. And this is not happening because of anything exotic. It is happening because there is no atmosphere to mediate. The sunlit side absorbs radiation and heats up dramatically. The shadowed side radiates its own energy away into space and cools dramatically. There is nothing in between to smooth out the difference. This is what happens when you take away the atmosphere that most of us have spent our entire lives inside of without ever really thinking about it. Now let us go back to Earth for a moment, because there is something worth understanding about why you feel warmth from the sun, even in cold weather, and why that feeling does not contradict any of what has been said above. When you stand outside on a clear winter day and the sun is out, you feel warmth on your face even when the air temperature is below freezing. This is direct radiative heating. The sun's radiation is hitting your skin and being absorbed and converted to heat. The air around you might be 20 degrees Fahrenheit, but your face is warmer than that because radiation is hitting it. This is exactly the same mechanism that would overheat a spacecraft. The sun is not heating the air between you and it. The sun is heating you. The air just happens to be sharing some of the warmth afterward, and your body is generating its own heat, and the whole system is in equilibrium in a way that makes it feel like ambient warmth. Strip away the air, Strip away the equilibrium, and you get the raw version of what radiation does. It heats surfaces. It heats materials. It heats objects that absorb it. It does not heat nothing, and space is as close to nothing as the universe offers. There is a popular image of space as a place where you would instantly freeze solid the moment you stepped outside a spacecraft. It is in movies. It is in books. It is in the way people casually talk about the void. It is not quite right. If you were exposed to the vacuum of space with no protection, the immediate threats are not primarily temperature. They are the vacuum itself, the absence of pressure, which would cause the gases dissolved in your blood to begin forming bubbles, a condition called ebullition. They are the absence of oxygen. They are the radiation. These would incapacitate or kill you in roughly 1 to 2 minutes without any suit. But you would not instantly freeze. Here is why. In space, heat can only leave your body through radiation, and radiation, while relentless over time, is not instantaneous. The human body is not a bad radiator, but it is not so efficient that it would shed its core temperature in seconds. The outer layers of your skin would cool relatively quickly, but your core temperature would take considerably longer to drop to dangerous levels through radiation alone. In fact, in direct sunlight, the bigger short-term concern might be the opposite. Your body absorbs solar radiation. Without sweating, without convection, without any of the cooling mechanisms that rely on atmosphere, you might actually experience heat stress on your sun-facing side faster than cold stress on your shadowed side. This is not a recommendation to go outside without a suit. The other problems would kill you long before temperature became the primary issue. But the point is that the intuition most people carry, that space is a place where cold is the immediate and overwhelming danger, misses the complexity of what thermal physics actually looks like in a vacuum. The astronauts on the International Space Station are not primarily fighting to stay warm. They are fighting to keep the station at a stable temperature at all, which means both preventing overheating in sunlight and preventing excessive cooling in shadow. The ISS has radiators, large panels that extend outward from the station and dump excess heat into space by radiating it away. Without those radiators, the electronics, the crew, and the equipment would overheat. The station generates heat internally from all its machinery and its crew, and that heat has to go somewhere, because in a vacuum it cannot just dissipate into the air the way heat dissipates in a building. This is one of the stranger aspects of being in space. The problem is not just cold. The problem is heat management. The engineers who design spacecraft spend enormous amounts of time and effort on what is called the thermal control subsystem, a collection of heaters, radiators, heat pipes, insulating blankets, and reflective surfaces designed to keep every component of the spacecraft within its operating temperature range at all times. Some components need to be kept warm. Battery systems and certain electronics can fail if they get too cold during periods when the spacecraft is in shadow or far from the sun. Heaters are installed specifically for those components. Other components need to be kept cool. High-powered electronics generate heat as a byproduct of operation. In space, that heat cannot be removed by blowing air over a heatsink the way a computer fan works on Earth. It has to be conducted away through the structure and then radiated away through dedicated radiator panels. The engineering challenge is not simply keep it warm or keep it cool. It is maintain a precise temperature range in an environment that alternates between intense solar radiation and complete shadow, where the only available heat transfer mechanism is radiation. That is a hard problem. And it is hard specifically because of the principle we started with. Space is not hot or cold in the way we usually mean those words. Space is empty, and that emptiness forces everything to manage its own temperature through radiation alone. When we talk about the temperature of space, we have to be careful about what we mean, because the phrase is doing a lot of work. If you ask what the temperature of interplanetary space is, near Earth, you might get an answer in the range of -270 degrees Fahrenheit. That number refers to the temperature that a theoretical perfect absorber, with no internal heat source, in the shade, would eventually reach by radiating its own energy away. It is the equilibrium temperature of an object in space that is not being heated by anything. But if you ask what temperature an object in direct sunlight near Earth reaches, the answer is completely different. A dark-colored object with high absorptivity and low reflectivity, like a piece of black material, could reach temperatures well above 200 degrees Fahrenheit in full sunlight at Earth's distance from the Sun. These two numbers are not contradictory. They describe different situations. One describes what happens when there is no heating. The other describes what happens when there is active solar radiation being absorbed. Space does not have a single temperature. Different objects in space have different temperatures depending on how much radiation they are absorbing, what they are made of, how efficiently they radiate heat away, and where they are. A spacecraft near Mercury, where sunlight is much more intense, has to manage far more heat than a spacecraft near Saturn, where sunlight is much weaker. The Cassini probe that orbited Saturn was engineered to deal with very little solar energy. The Parker Solar Probe, which flies close to the Sun, has a heat shield capable of withstanding temperatures of nearly 2,500 degrees Fahrenheit, because at that proximity, the solar energy is intense enough to produce those temperatures on the surface of the spacecraft. Same empty space, radically different thermal environments, because the emptiness of space itself has no temperature worth speaking of. Only objects have temperatures, and objects in space can range from almost absolute zero to several thousand degrees, depending entirely on their relationship to radiation sources. Now we get to the deep end, because so far we have been talking about space near our Sun, within the solar system. What about the space between stars? What about the space between galaxies? Out there, the Sun is a distant point of light. Its contribution to heating anything is negligible. The question becomes, what temperature an object would reach with no significant radiation source nearby? The answer is very close to absolute zero, but not quite absolute zero. And the reason it is not quite zero is one of the most remarkable facts in all of cosmology. The universe is not completely dark. Everywhere in the universe, in every direction, there is a faint glow of microwave radiation. This is called the cosmic microwave background radiation, and it is the afterglow of the Big Bang, the remnant heat of the universe's birth stretched and cooled over 13.8 billion years of expansion. This radiation fills all of space uniformly. There is no direction you can point an antenna where you would not detect it, and it corresponds to a temperature of approximately -455 degrees Fahrenheit, or about 2.7 Kelvin above absolute zero. This is the baseline temperature of the universe. An object in deep space, far from any star, far from any galaxy, would eventually cool to 2.7 Kelvin through radiation. It would not reach absolute zero because the cosmic background is always there, always delivering a tiny amount of energy from every direction. 2.7 Kelvin is extraordinarily cold. It is colder than any environment naturally occurring on Earth. It is colder than any experiment most laboratories can produce without specialized equipment. It is a cold that makes the coldest winter night on Earth feel like a sauna. But it is still not zero, and it is still a temperature produced by radiation, not by the emptiness of space itself, but by the residual electromagnetic signature of the event that created the universe. Even at the very edge of everything, heat is still radiation, and radiation is still the only mechanism available to move energy through a vacuum. Bring all of this together, and the original question answers itself. Why is space cold if the Sun is so hot? Because the Sun heats by radiation, and radiation heats surfaces, not empty space. The 150 million kilometers between Earth and the Sun is not a corridor of warmth. It is a corridor of light, of electromagnetic energy traveling at the speed of light through a vacuum that is almost completely empty. That light does not warm the corridor. It travels through the corridor and warms whatever it hits at the end of it. The Earth absorbs that radiation. Its surface heats up. Its oceans absorb it and release it slowly. Its atmosphere traps some of it and moderates the temperature across the surface. The result is an average surface temperature comfortable enough to support liquid water and life as we know it. A spacecraft absorbs that radiation on whatever surfaces face the sun. Those surfaces heat up. The surfaces in shadow cool toward the baseline of deep space. The engineering team managing the spacecraft fights constantly to keep the whole machine within functional temperature ranges. The moon absorbs that radiation with nothing to mediate it. The sunlit side bakes. The shadowed side freezes. The temperature difference between the two, separated sometimes by nothing more than a boulder's shadow, can exceed 500 degrees. And the space between it all, the space between Earth and Moon, between Earth and Sun, between Sun and the nearest star, between galaxy and galaxy, that space is not hot or cold in any meaningful sense. It has almost no matter in it to have a temperature. It has no air to warm or cool. It is not a room you can heat up or cool down. It is an absence, a stage without props. Space is not cold. Space is not hot. Space is almost nothing, and almost nothing cannot be warmed. The sun is blazing. The light is real. The energy is extraordinary, but the stage it crosses to reach us holds none of it. The energy moves through the emptiness without touching it, and only when that light finally hits something, a planet, a moon, a spacecraft, a human face turned toward the sky, does the emptiness give way to heat. Space is not a cold room. Space is an empty stage, and the sun heats not the stage, but everything standing on it. There is another layer to this that rarely gets discussed, and it changes the way you think about the sun itself. When we say the sun is hot, we are compressing an enormous amount of complexity into a single word. The sun is not one temperature. It is a system of wildly different temperatures at different layers, and the relationship between those layers is one of the strangest things in astrophysics. The surface of the sun, called the photosphere, is where sunlight originates. The temperature at the photosphere is approximately 10,000 degrees Fahrenheit. That is hot enough to vaporize any material humans have ever worked with. But it is not the hottest part of the sun. Above the photosphere is a thin layer called the chromosphere, and above that is the corona, the outermost atmosphere of the sun that stretches millions of kilometers into space, and that you can see during a total solar eclipse as the ghostly white halo surrounding the darkened disk of the moon. The corona is dramatically hotter than the surface below it. While the photosphere sits at around 10,000 degrees Fahrenheit, the corona reaches temperatures between 1.8 million and 3.6 million degrees Fahrenheit. In places, it can spike even higher during solar events. This is physically bizarre. It is as if you walked away from a fire and found that the air got hotter the farther you moved from the flames. It violates intuition completely. Heat should diminish with distance from its source. The reason this happens is still not completely understood. It is one of the open problems in solar physics, called the coronal heating problem. The leading hypotheses involve magnetic wave activity, magnetic reconnection events releasing bursts of energy, and small-scale heating events called nanoflares. But no single explanation has been definitively proven. What this means for the question of space temperature is interesting. The solar wind, the stream of charged particles the sun constantly exhales outward in all directions, carries material from the corona. Near Earth, the solar wind arrives at speeds between 250 and 750 kilometers per second. And the particles in that wind carry energies corresponding to temperatures in the millions of degrees. So technically, the interplanetary medium near Earth is filled with particles that are extraordinarily hot by any conventional measure. And yet you would not feel warm floating in it, because the density is so extraordinarily low. There are roughly 5 to 10 particles per cubic centimeter in the solar wind near Earth. For comparison, The air at sea level on Earth contains approximately 30 quintillion molecules per cubic centimeter. The solar wind near Earth is about 6 quintillion times less dense than the air you are breathing right now. Temperature and heat are related but different things. Temperature measures the average kinetic energy of particles, how fast they are moving. Heat measures the total thermal energy in a system, which depends on both the temperature of the particles and how many of them there are. The particles in the solar wind near Earth are moving very fast, which means they have high temperature. But there are so few of them that the total heat they carry is negligible. If you were floating in the solar wind, you would not feel warm, because there are not enough particles colliding with you to transfer meaningful amounts of energy to your body. This is the same reason that the upper atmosphere of Earth, the thermosphere, which sits roughly 60 to 300 miles above the surface, can reach temperatures of several thousand degrees Fahrenheit, while simultaneously being a place where you would freeze. The air is so thin up there that the high-speed molecules almost never collide with each other or with anything else. The temperature is high, but the heat content is almost zero. Temperature without density is a number without consequence. Space near the sun is full of very hot particles, but hotness without substance cannot warm anything. Astronauts live inside this paradox every single day of a mission. The International Space Station maintains an internal temperature of roughly 65 to 80 degrees Fahrenheit. This is accomplished not by passively absorbing the sun's energy, which would be far too much heat for comfort, but through an active thermal control system that is one of the most sophisticated engineering achievements aboard the station. The outer surface of the ISS is covered in a variety of materials selected specifically for their thermal properties. Some areas use multi-layer insulation blankets, sometimes called space blankets, which are highly reflective and reduce both heat absorption and heat radiation. Some surfaces are painted specific colors, not for aesthetics, but because color directly controls how much solar radiation a surface absorbs and how much it emits. White and silver surfaces reflect more and absorb less. Dark surfaces absorb more and emit more. Inside the station, all the electronics, the lighting systems, the life support systems, the experiments, the crew themselves, all of these generate heat continuously. In a building on Earth, that heat would dissipate through the walls, through ventilation, through the movement of air to the outside. On the ISS, that is not possible. The heat has to be collected and moved. The station's thermal control system uses ammonia as a coolant, pumping it through pipes embedded in the station's structure. The ammonia absorbs heat from the interior systems and carries it out to large radiator panels mounted on the station's truss. Those radiator panels face away from the sun and away from Earth, pointing into the cold of deep space. They glow in the infrared as they dump the station's waste heat into the void. Without those radiators, the ISS would overheat within hours. The sun adds heat. The crew and equipment add heat. With nowhere for that heat to go, temperatures would rise until systems began failing. The challenge of staying warm in space is, for the ISS, far less pressing than the challenge of staying cool. This surprises people. The mental image of astronauts struggling against the cold of space is pervasive, and it is not entirely wrong, because certain components and certain scenarios do require heating. But the dominant thermal challenge for a crewed station in low Earth orbit, bathed in sunlight for much of each orbit, is heat rejection, not heat generation. The suits astronauts wear during spacewalks deal with the same challenge in miniature. The suit has to protect the astronaut from the vacuum, from radiation, and from temperature extremes. It includes a liquid cooling and ventilation garment, essentially a network of tubes through which water circulates, absorbing heat from the astronaut's body and carrying it to a system in the suit's backpack that releases it into space. Astronauts working hard during a spacewalk, performing physical tasks in the bulky suit, generate considerable body heat. Without active cooling, they would overheat. The suit also has heaters for the hands and extremities, because in shadow, those surfaces can cool rapidly toward dangerous temperatures. And the suit's outer layer uses carefully selected materials to balance heat absorption and heat emission to keep the whole system within survivable ranges. Every spacesuit is a miniature thermal engineering project. Every spacecraft is a larger one. The fundamental challenge is always the same. Radiation is the only game available, and you must learn to play it in both directions simultaneously. There is a question underneath all of this that is worth sitting with for a moment. Why do we find this confusing at all? Why does the cold of space seem to contradict the heat of the sun when the physics, once understood, is clean and consistent? The answer is probably that all of human intuition about temperature was built inside an atmosphere. We evolved on a planet wrapped in a layer of gas that conducts heat, convects heat, holds heat, and distributes heat in ways so continuous and so pervasive that we never noticed we were depending on them. The warmth of a summer day is not just radiation from the sun. It is radiation absorbed by the ground and re-emitted. Radiation absorbed by water vapor and re-radiated. Heat convected upward from warm surfaces and mixed through the atmosphere. The ocean releasing stored heat it absorbed weeks ago in a different part of the world. When we step outside and feel warm, we are feeling the output of an enormously complicated heat management system that the Earth has been running for 4 billion years. We are not feeling the sun directly. We are feeling the Earth's response to the sun, mediated through an atmosphere and an ocean and a biosphere that we have never had to think about because we have never been anywhere else. The cold of space is not strange. The warmth of Earth is what required explanation. We just never needed the explanation because the warmth was always simply there. Taking away the atmosphere, the ocean, and the biosphere, and asking why things are different is like taking away a building's heating system and asking why it is cold inside. The heating system was doing something. It was not the default state. The default state, in the universe as a whole, is very close to nothing. The Sun is one of roughly 200 billion stars in the Milky Way alone. The Milky Way is one of roughly 2 trillion galaxies in the observable universe. Most of the volume of the universe is not near a star. Most of the volume of the universe is the deep intergalactic medium, the space between galaxies, where matter is so sparse that measuring it requires describing it in terms of a few atoms per cubic meter, rather than the roughly 30 quintillion molecules per cubic centimeter we have here at sea level. In that intergalactic space, the cosmic microwave background is essentially the only radiation present. The temperature of the background, 2.7 Kelvin, is as cold as a place can be while still having anything at all to measure. Stars are the exceptions. Warmth is the exception. The baseline state of the universe is a cold so profound it makes our most extreme laboratory experiments look warm. The sun burns at millions of degrees at its core and tens of thousands at its surface. It has been burning for 4.5 billion years and has enough fuel for another 5 billion. It fills a volume so large that over 1 million Earths could fit inside it. And the energy it releases every second dwarfs anything humans have ever produced or imagined producing. All of that is real. The power of the sun is not in question, and yet the vast majority of the space it illuminates is indifferent to it. The photons travel. The vacuum receives them with no reaction. Only the rare object, a planet, a moon, an asteroid, a spacecraft, a comet, catches them and converts them into something you could call warmth. The universe is not heated by its stars. The universe is dotted by them. And between the dots, the emptiness goes on and on. Cold, not because cold was imposed on it, but because cold is what you get when there is nothing there at all. There is one more thing worth understanding about how the sun's energy moves, because it makes the whole picture more complete. Not all of the sun's radiation is visible light. The sun emits across an enormous range of the electromagnetic spectrum, from radio waves at the low energy end, all the way to X-rays and gamma rays at the high energy end. What we call visible light the part of the spectrum our eyes evolved to detect, is actually a relatively narrow band in the middle of everything the sun is putting out. A significant portion of solar energy arrives as infrared radiation, which is the part of the spectrum we associate directly with heat. When you stand near a campfire and feel the warmth on your face even without touching the flames, that is largely infrared radiation being absorbed by your skin. The sun delivers infrared too, and it is absorbed by surfaces differently than visible light is. Some materials that appear transparent to visible light are opaque to infrared. Glass is a good example. You can see through a glass window, but glass blocks much of the infrared radiation trying to pass through it. This is the principle behind a greenhouse. Visible light passes through the glass roof and is absorbed by the plants and soil inside. That energy is then re-emitted as infrared. But the infrared cannot pass back out through the glass. It is trapped inside, and the greenhouse warms up. The Earth's atmosphere works on the same principle at a planetary scale. Carbon dioxide, water vapor, methane, and other gases in the atmosphere are transparent to incoming visible light, but absorb outgoing infrared radiation. Energy comes in as visible light, is absorbed by the surface, and is re-emitted as infrared. The infrared is trapped by the atmosphere. The surface warms. This is the greenhouse effect, and it is the reason Earth's average surface temperature is about 59 degrees Fahrenheit, rather than the -0 degrees Fahrenheit it would be without any atmosphere at all. The atmosphere is not generating heat. It is slowing the rate at which heat escapes into space. It is a blanket, not a furnace. Remove that blanket, as happened on Mars billions of years ago when its atmosphere thinned dramatically, and the surface cools toward what radiation alone would produce. Put a thicker blanket on, as appears to have happened on Venus at some point in its ancient past, and the surface heats to temperatures that melt lead. The same fundamental principle: radiation in, radiation out, and the atmosphere mediating how quickly the exchange happens. In space, there is no blanket. There is no mediation. There is only the radiation arriving and the radiation leaving, and the object in between managing both as best it can. So the next time you look at the sun and feel its warmth on your face, consider what is actually happening. Photons left the sun about 8 minutes ago. They traveled 150 million kilometers through a near-perfect vacuum without warming a single cubic centimeter of it. They passed through the upper atmosphere, where particles move at the energies of millions of degrees, but are too sparse to heat anything. They entered the lower atmosphere, where the air absorbed some of them, and scattered some of them, and let some of them through. And then they hit your face. Your face absorbed them. Your skin converted that electromagnetic energy into thermal energy. Your blood carried some of that warmth to the rest of your body. Everything between the sun and your face was indifferent to the transaction. The warmth was never in the space between. The warmth was always only in the thing that caught the light. Space is not cold the way a winter's night is cold. Space is not cold the way a freezer is cold. Space is not cold because someone turned down the heat. Space is empty. And emptiness is not cold. It is nothing at all. The sun heats the stage. No, the sun cannot heat the stage. The stage is not there to be heated. The sun heats everything standing on it, and in between the things standing on it there is only the light, crossing the dark, waiting for something to land on.